Hey, what's up, guys? This is Dr. Vivek Palipuram, and I'm bringing you the next lecturette in ENGR 250 Probability and Statistics for Engineers and Computer Science. In this lecturette, I'm going to discuss conditional probability and event independence. Now, conditional probability occurs quite frequently in science and engineering because oftentimes engineers and scientists try to make sure that the thing that they're looking for is in a reduced sample space. Specifically, the definition of conditional probability is as follows. Conditional probability is a modified probability of event A because some other event B has happened. Now, because this other event B has happened, the event A is now observed in the reduced sample space. Now, because event A is observed in the reduced sample space, the probability of event A may possibly be increasing now because our sample space has reduced. You may have applied conditional probability implicitly in your day-to-day life and in fact in your academic life as well. Now, I can guarantee you that many of you must have asked your professor, hey professor, do you think this portion is important for the final exam? And the professor is going to tell you yes or no. And based on that, you are essentially reducing the sample size of the amount of syllabi that you need to cover. Essentially, you're reducing the sample space of the syllabi that you need to cover, and in this way, you're improving your chances of getting higher grades or scoring maximum marks in your respective exams. Conditional probability may also play against you at some times. For example, a reduced sample space does not always imply that probability of event A might increase. For example, let's say that you come to the professor and ask the professor, hey, professor, what's the probable, what are the chances that I got an A grade, or did I get an A grade or not? And now, if your professor is probability savvy, they may tell you, hey, you know what, you got a grade which is less than B plus. So in this way, probability of event A, meaning you getting an A grade happening, is actually zero now, because now your sample space has reduced in such a way that it has completely excluded the event A. In this way, conditional probability affects the probability of any event A. Depending on how the sample space is reduced, it may either increase the probability of event A or it may decrease the probability of event A. Now let's solidify this example or the theory of conditional probability using an intuitive example. Let's say that I have a six-sided die, it's a fair die, and I roll it. And let's say that I do not show you what number has come up, but instead I tell you that a number greater than 3 was rolled. And then I ask you, what's the probability that an event number was rolled? You can pause your video here and think about this problem. I roll a die, I do not tell you what number has come up, but I tell you that a number greater than 3 was rolled. What is the probability that you rolled an even number? You can pause your video, think about it. Once you're ready to proceed ahead, you can unpause the video and I can show you how this problem is solved intuitively. Okay, I hope you guys got the chance to look into this problem and solve it in your own head as to what should be the probability for an even number to be rolled if given the information that a number greater than 3 was rolled. Now, in this problem, you must have implicitly reduced, or in your head, you must have reduced the sample size or the sample space. For example, in this case, I tell you that a number greater than 3 was rolled. So immediately in your head, you're like, okay, either 4, 5, or 6 must have been rolled. Either 4, 5, or 6 must have been rolled because a number greater than 3 was rolled. And then you're interested in even number was rolled, and even numbers happen to be 4 and 6. So there is 2 in 3 chance that an even number was rolled given that a number greater than 3 was rolled. So that's how you must have solved this problem using conditional probability. You must have first obtained a reduced sample space, and then you looked into the favorable outcomes in this reduced sample space, and you must have applied theorem 1.a implicitly here, which is the cardinality of the event of interest in the reduced sample space, which happens to be 4 and 6. So the cardinality of this event is equal to 2, and the size of the reduced sample space. The reduced sample space is 4, 5, and 6. So the size of the reduced sample space is 3. So you got the probability 2 or 3. Now, this intuitive example only works if all of the outcomes in the sample space are equally likely. So this example will only work, or this theorem in this case for conditional probability will only work if all the outcomes are equally likely. But that is never always the case. Sometimes some of the outcomes have different probabilities. So we need to obtain a nice mathematical formula for conditional probability that can be applied all the time. So let's look into the mathematical expression for conditional probability. So conditional probability, we are always interested in finding the probability of event A given that event B has happened. In mathematics, we write this as follows: probability of event A given that B has happened. So this is your given operator, so to speak, in mathematics, probability of A given B. Now, because event B has happened, B happens to be your reduced sample space. B happens to be a reduced sample space, and we are interested in how much A has happened in this reduced sample space. So essentially, we are looking at event of interest in the reduced sample space, and that is A intersection B. So probability of A given B is probability of A in the reduced sample space divided by the probability of B, which is your reduced sample space. Now, this formula for conditional probability will work all the time. And my recommendation is try to use this formula as much as possible. Intuitively solving conditional probability may work, but sometimes that may give you an incorrect result should you not apply your intuition properly. This formula, probability of A given B is equal to probability of A intersection B or probability of B, is going to work all the time. So my recommendation is use this formula all the time. Now let's look into some theorems with respect to conditional probability. Conditional probability at the end of the day is a probability. So probability of A given B will always be greater than or equal to 0. Probability of B given B is always equal to 1, because you're asking, hey, what's the probability that event B has happened given that event B has happened? Well, the answer is 1. If A is written as a union of multiple sets, then probability of A given B is equal to probability of A1 given B plus probability of A2 given B, and so on until probability of AN given B, provided that each of these events are mutually exclusive. Now it's time for us to actually work on an example on conditional probability. So here's what I would like for you guys to do. I would like for you guys to carefully read this problem statement. Let's say that this a priori event that at least one video packet has arrived is event E. Here we need to find probability of A given E, we need to find probability of B given E, and we need to find probability of C given E. So first, before I give you the solution, what I would like for you guys to do is pause your video here and enumerate the samples or the outcomes in this event E. Now notice here that we are receiving sequence of 3 packets, where each packet can be either an audio packet or a video packet. So the possible sequences are AAA, AAV, AVA, and so on. So there are going to be 8 such outcomes. So what I would like for you guys to do is elucidate all of the outcomes in the sample space and elucidate the outcomes in this event E, that at least one video packet has arrived. Once you're ready, you can unpause the video and I can show you how to solve this example. Okay, I hope you had the chance to look into this problem and give it a shot as to what should be the outcomes in the sample space S and this event E. Let's read this problem one more time. You receive a sequence of 3 packets. Each packet can be either a data packet A or a video packet V. Sequences AAA, AV, AVA, AVV, VAA, VAV are equally likely with probability 0.1, and sequences VVA and VVV have probability 0.2 each. And it is given to us that at least one video packet has arrived. So that's our event A. And we need to find probabilities of events A, B, and C given that A has happened. So let's work on this problem and apply the conditional probability formula. So first things first, I'm going to elucidate my entire sample space. Now each packet can be either audio or video, and I'm receiving 3 packets. So I can receive AAA, AAV, AVA, AVV, VAA, VAV, VVA, and VVV. Essentially, I'm elucidating numbers 000, 001, 010, 011, and so on until 111. I'm just elucidating the binary numbers from 0 to 7. So it's given to you here that the probability of AAA is 0.1. This is 0.1, 0.1. AAV is also 0.1, VAA is 0.1, VAV is 0.1, whereas VVA and VVV are 0.2 each. So these are the outcomes and their respective probabilities. Now, if you carefully observe, probability of S will be equal to sum of the probabilities of these outcomes, and you will notice that it will come up to be equal to 1, which should be always true. Probability of the sample space is always equal to 1. It's given to you that event E has happened where I have at least one video packet. So let's elucidate the outcomes of this event E, at least one video packet. I have at least one video packets in all of these cases except for AAA. So event E is comprised of outcomes AAV, AVA, AVV, VAA, VAV, VVA, and VVV. And these have probabilities 0.1 from here. From these probabilities, I have 0.1, 0.1, 0.1, 0.1, and these two are 0.2 each. So probability of event E now is equal to sum of the probabilities of these outcomes. So I need to add probability of AAV, probability of AVA, and so on until probability of VVV. And if I were to perform this math, I'll get 0.1 plus 0.1 plus 0.1, 0.1, 0.1. So that's 0.5 plus 0.4, giving me 0.9. So that's the probability of event E, that at least one video packet has arrived. I need to find the probability of A given E, where event A is at least 2 video packets. So let's see where exactly we have at least 2 video packets, or what outcomes comprise the set at least 2 video packets. I have at least 2 video packets in AVV, I have at least 2 video packets in VAV, in VVA, and I have at least 2 video packets in VVV. I have 3 video packets here, so it satisfies the condition of at least 2 video packets. Probabilities of these outcomes are 0.1, 0.1, VVA is 0.2 and 0.2. So probability of A is equal to 0.1 plus 0.1 plus 0.2 plus 0.2, which is equal to 0.6. But here I need to find probability of A given E. So probability of A given E is probability of A intersection E, or probability of E. So let's find an intersection first between A and E. Intersection essentially is what are the common items or common outcomes to both of these sets. A has AVV, so does set E. So AVV is a member of both. VAV, A has VAV, so does E. A has VVA, so does E. A has VVV, so does E. So essentially, A intersection E is my entire set A, because A is entirely contained in set E. So I can write this as probability of A intersection E is equal to probability of A, which is equal to 0.6. So probability of A given E is 0.6 divided by 0.9, giving me 2/3. So that's the probability of event A. You can pause your video here and carefully go through the solution. Once you're ready, you can unpause your video, upon which time I will erase whatever I have written and solve part B for you. All right, so I hope you had the chance to look into the solution. Next, I need to find the probability of event B, which is last packet is a video packet, given that event E has happened. So I'll erase everything except for calculating the probabilities of event E. So I'll erase this portion here because I need to work on probability of event B. Now event B is totally different. Event B is last packet is a video packet. So let's work on part B. Last packet is a video packet. Last packet is video. So let's elucidate the outcomes in this set B. And those outcomes are AAV, AVV, VAV, and VVV. These are the only outcomes where the last packet is a video packet. Last packet is a video packet. Probability of AVV is given to you in the problem statement that it is 0.1. Probability of AVV is also 0.1. Probability of VAV is 0.1 and probability of VVV is 0.2. So that's event B. I need to find probability of B given E, and by conditional probability formula, I can obtain it as probability of B intersection E or probability of E. I've already found probability of event E. I need to find probability of B intersection E. So let's find what B intersection E actually is. Essentially, what are the common items between B and E? B has AAV, so does sample space S. It also has AAV. B has AVV, so does sample space S. My apologies, so does event E. I need to find the common items between set B and E. So let me work this one more time because my thoughts got derailed there for a second. B has AAV, so does E. B has AVV, so does E. B has VAV, so does E. And B has VVV, so does E. So essentially, B is also entirely contained in set E. So probability of B intersection E is going to be equal to sum of probabilities of these outcomes. So 0.1, 0.1, 0.1, 0.2. So that gives you 0.5. Because if you add these guys together, it will give you 0.5. So probability of B given E is 0.5 or 0.9, giving you 5/9. Now let's solve part C now. So I'll solve part C. So to solve part C, I'll just erase all of this because I don't need it. Part C is interesting in the sense that now I'm counting the number of video packets, and the number of video packets has to be exactly equal to 2. That's what part C is all about. Okay, so part C, event C is number of video packets is equal to 2. So let's elucidate the outcomes. Where exactly do I have 2 video packets? I have 2 video packets in AVV. I have 2 video packets in VAV, in VVA, and that's about it. These are the only outcomes where I have exactly 2 video packets because NV is defined as the number of video packets. AVV has probability 0.1, VAV has probability 0.1, VVA has probability 0.2. I need to find probability of C given E, which can be found as probability of C intersection E or probability of E. So let's find out the items that are common between C and E. C has AVV, so does E. C has VAV, so does E. C has VVA, so does E. So again, C is entirely contained in set E. So probability of C intersection E will be equal to the sum of the probabilities of these outcomes, which is equal to 0.1 plus 0.1 plus 0.2, which is 0.4. So probability of C given E is equal to 4/9. So that's how you apply the conditional probability formula to solve probability problems. There's another example that I would like for you guys to work on, and that's example number 2. In this example, you have shuffled deck of 3 cards, 2, 3, and 4. You deal out 3 cards. Let E of I denote that ith card dealt is an even number. What's the probability of E2 given E1? What I'll do is I'll just solve part A for you, and part B and C, you're going to solve it on your own. I do not expect you to turn parts B and C, but I would like for you guys to work on parts B and C. So in this problem, I have a shuffled deck of 3 cards, 2, 3, 4, and shuffle them well. And I deal out 3 cards. So there are different ways in which the cards can be dealt. I can deal the card as 2, 3, 4. I can also deal it as 2, 4, 3. I can deal it as 324, I can deal it as 342, or I can deal it as 423 or 432. So there are 6 possibilities here. And because the cards are well shuffled, I can assume that each of these outcomes is equally likely. And since the sample size's cardinality is equal to 6, probability of any one given outcome is 1 over 6. Because I have n is equal to 6 outcomes, so I'm going to apply my theorem 1.5. So each of these outcomes are equally likely with probability 1 over 6. In part A, I need to find probability of E2 given E1, which can be obtained using conditional probability as E2 intersection E1 or probability of E1. So let's find out what are the outcomes in events E1 and E2 and also E2 intersection E1. So E1 event is defined as the first card dealt is the even numbered card. The ith card is the even card. So the first card is the even card. So the outcomes are 234, 243, 423, and 432. So these are the outcomes in probability in event E. Each of these outcomes has probabilities 1 over 6 obtained right here. So probability of event E1 is equal to the sum of the probabilities of these outcomes. So that gives me 4 over 6. I need to find E2 now, or the outcomes in E2. Second card is an even card. So I have second card as even card here because 4 is even. And the second 4 is the second card in this case. So that's even. 3 to 4 is a valid outcome. 3, 4, 2, and similarly 4, 2, 3. And each of these outcomes is equally likely with probability 1 over 6 given right here. So I don't have to find the probability of event E2 to get the conditional probability in this case. I do need to find out what E2 intersection E1 is. What are the items that are common to both E2 and E1? E1 has 234, but E2 doesn't have it. E1 has 243, E2 also has it. E1 has 423, E2 also has that. And that's about it. So these are the only 2 outcomes that are common to both E2 and E1. So probability of E2 intersection E1 is equal to the sum of the probabilities of these outcomes, which is 1 over 6 from right here, from the sample space. So when I add them, I get 2 over 6. So probability of E2 given E1 is equal to 2 over 6 divided by 4 over 6. That gives me 1/2. So that's how you apply conditional probability to solve probability problems. What I would like for you guys to do is solve parts B and C on your own. Should you have any questions, please join me during my WebEx office hours. I do not expect you to submit this problem. Now, this problem will be solved by you and you'll be also uploading your solution on Canvas. I will open up an assignment page on Canvas along with the problem from the previous lecturette. You're going to turn this in as well. Before I end this lecturette, there is one last item that I wanted to cover, and that was independent events. So let's talk briefly about what independent events are all about. So let me erase this portion here. I can use this for explaining what independent events are. 2 events A and B are said to be independent if the occurrence of one event in no way affects the probability of the other event. So let me formally introduce what independent events are. A and B are independent if occurrence of B does not alter probability of A. Now, as so far in conditional probability, we have been studying that because event B has happened, probability of event A may alter. But if A and B are independent, then occurrence of event B does not change probability of A. So probability of A given B remains unaffected to probability of A. So probability of A given B is equal to probability of A. For this conditional probability expression, I can apply this formula, probability of A intersection B or probability of B is equal to probability of A. So when 2 events are independent, then probability of A intersection B is equal to probability of A times probability of P. You're going to use this expression to find out whether two events are independent or not. Sometimes event independence is not apparent. For example, if I were to take two coins, if I were to if I were to take a coin and if I were to toss two times, toss one and toss two, they are independent of each other because probability of getting a heads on toss two is in no way affected by what my outcome was in the very first toss. So it is apparent here that the two events are independent of each other, that these two tosses are independent of each other. But in science and engineering, sometimes we have a complicated experiment where it is not apparent whether or not two events are independent of each other or not. So in such cases, it's always advisable for us to obtain the probabilities of those individual events, obtain the probability of their intersection, and find out whether this equation holds or not. If this equation holds, then the two events are independent of each other. We are going to solve such problems later ahead. I think it's a good time to stop this lecturette. Thanks for listening.